Allan Greenleaf from University of Rochester. We're going to talk about Introduction to FIOs Lecture 1.
Okay, thank you. So the three lectures that Luca and I will be giving today and tomorrow are building on top of what Shu Wen and Andras did yesterday for pseudo-differential operators. We will have a slightly different point of view. This will be totally in the realm of homogeneous microlocal analysis. I know many people here work in semi-classical microlocal analysis. At the end of the third lecture, and these lectures will be available online, at the end of the third lecture there will be a reading list and there will be some semi-classical references there. Okay, so I want to begin by talking about examples of FIOs, but just very broadly speaking, FIOs include the class of pseudo-differential operators, but they are much more general, and they've turned out to be very, very useful for things which they maybe were not originally intended for. So back in the 60s, there was work done using preliminary versions of FIOs, what were called canonical operators, which I'll write down later. And they're very useful for analyzing PDEs. As it turns out, the level of generality and flexibility that Hormander built into his general theory of FIOs in the early 70s, together with Dorstemat, really allowed FIOs to be applied to problems outside of PDE. So things like generalized Radon transforms, inverse problems, other things as well. So what I'll be doing is covering really the basics of homogeneous FIO theory circa the 1970s. However, that's really the foundation for many applications that are still ongoing. Right? Okay, so we'll give examples of FIOs before we define them. In fact, we won't even define them today. We'll talk about the wavefront sets of distributions, which already was discussed in yesterday's talks on SIDOs. We'll do it in a slightly different framework. And the Hormander-Sato Lemma, which says how linear operators with certain Schwartz kernels transform wavefront sets of the distributions that they act upon. We'll talk about an important preliminary class of Fourier integral distributions, what are called conormal distributions, which are commonly encountered and can be discussed on their own. And then we're going to talk about more general oscillatory integrals, which you need to do in order to talk about Fourier integral distributions and Fourier integral operators and their wavefront sets. And that will conclude this morning's lecture. So again, this is going to be totally in the context of homogeneous microlocal analysis. And furthermore, nothing is going to be compactified. So this is just sort of in the classical setting, or in fact, you do go to infinity. Okay, so let's look at some examples of FIOs. So to begin with, there are the pseudo-differential operators that were described yesterday. So they're given as oscillatory integrals, which in general don't converge. And so you have to have a way of interpreting what that means. And we'll do that later on in the talk. You have a phase function x minus y dot theta. Here, for the moment, x and y are ranging over open subsets of Rn. In general, of course, you can do this on manifolds. And you have a so-called amplitude A of x, y, theta, which belongs to a certain symbol class. And a little bit later, I'll define the two symbol classes that we'll be using. For all intents and purposes, this is the same symbol class that was used by Shu Wen and Andras yesterday, with some slight variation. Okay, so you have SIDOs. Okay? Now, the prototypical SIDO, in some sense, is multiplication by a smooth function. That's a zeroth order SIDO. What is sort of the prototypical FIO that's not a SIDO? Well, one argument is that the most basic example is composition with a diffeomorphism. If you have two open subsets of Rn, or again, more generally, two manifolds, and you have a diffeomorphism chi between them, if you pull back a function or you pull back a distribution by that diffeomorphism, that, which can be interpreted as a change of variables, is an FIO, but it's not a pseudo-differential operator because it moves singularities around. And using the Fourier inversion formula, you have the oscillatory representation down there at the bottom. If I can get this to work. I should say, by the way, that in all of the applications of the Fourier inversion formula, I really don't care about powers of 2 pi, so often the 2 pi's won't be there. So for all intents and purposes, this simply has the phase function chi of x minus y dot theta, which of course is different from this phase function. And again, it has an amplitude which is essentially 1 as a function of the phase variable theta. Okay. Now, just because the phase function looks different from the SIDO doesn't mean a priori that it's actually not a SIDO, but in fact, when chi is non-trivial, this is not a SIDO, as we'll see. Okay, now one of my favorite operators, which is the Radon transform, which has been enormously generalized to generalized Radon transforms. So of course, this is classical. It goes back to Radon's paper in 1917. So you are looking at a nice function on Rn to start with, although you can extend this to distributions, say, of compact support. And you look at all the hyperplane integrals of that function. So we let m sub n minus 1n denote the n minus 1 dimensional affine planes in Rn. And that can be parametrized in a 2-to-1 fashion as the sphere cross R, simply because you can describe any affine hyperplane as a set of y such that y dot omega equals s, where omega is a unit vector and s is some real number. Of course, in this description, if you replace omega s by negative omega minus s, you get the same hyperplane, but let's ignore that. So the space of affine hyperplanes is this, you can think of it as a cylinder, the sphere across R. And the Radon transform turns a nice function or distribution on Rn into a function on the sphere across the row line by simply integrating f with respect to n minus 1 dimensional Lebesgue measure on that hyperplane. And one can show that this makes sense even for fairly singular distributions f. And there's a classical representation of this, again using Fourier inversion, which is with the phase function e to the I y dot omega minus s times theta, where theta is now a one-dimensional phase variable. And again, up to constants, the amplitude is just 1 of theta, which is a symbol of order 0, d theta dy. Right? So this is sort of the form that an FIO is going to take. It's going to be e to the I, a phase function satisfying certain first and second order conditions. There'll be a reasonably nice amplitude, and you integrate against the function or distribution, and you transform it into a new one. And the question is, how do they come up? What are they good for? What estimates do they satisfy? What kind of algebraic properties do they have, etc. And what will be important is that the phase function encodes a certain geometry, and that geometry, depending on how nice it is, allows you to have good estimates or good algebra or not. Right? And so some of the interesting problems in the field are what happens when you have degenerate FIOs, where the basic conditions for an FIO are satisfied, but the conditions for some of these other properties are violated. But the Radon transform is a very nice FIO. Okay, a similar operator, but using curved surfaces rather than hyperplanes, is the spherical mean operator, which is important for solving the wave equation and is also much beloved by harmonic analysts. So this simply is the following. Fix a radius t bigger than 0. You can take t equals 1 if you want. And you define the convolution operator on Rn, which is simply convolution with surface measure on the sphere of radius t, which you can normalize if you want to, but you don't have to. And in fact, because this measure on the sphere has compact support, in fact, this is convolution with a distribution of compact support, and therefore maps distributions to distributions. And it's given by this formula here. And if you write it down as an oscillatory integral, using the fact that the defining function for the sphere of radius t centered at the point x in terms of the variable y is x minus y, length of x minus y minus t, you have this oscillatory representation. So again, a phase function and amplitude integrating against f of y dy d theta. And again, in this representation, theta is just a one-dimensional phase variable. Okay. Another example is a modification of the Radon transform due to Melrose and Taylor in work they did in the 80s on scattering for waves in the time domain by strictly convex obstacles in Rn. They looked at the so-called corrected Kirchhoff approximation. And so you do the following. You let omega be a domain in Rn with C infinity strictly convex, meaning positive curvature boundary of omega. And now you define a transform which turns distributions on the cylinder, which is the boundary of omega across R, into distributions on the other cylinder, which is the sphere across R. Right? You define in the following way. You take F, which is a function of y and s, y in the boundary and s a real number, and you integrate it over the surface y dot omega equals t minus s. So this is basically a slanted hypersurface in the cylinder. So here's omega. There's boundary omega, and the cylinder is boundary omega across R. And so what this does is, depending on the values of omega and t, it integrates over a slanted surface inside of the cylinder, a hypersurface inside of the cylinder. So it's an example of what's called a generalized Radon transform. And it's given simply by that representation. But it turns out that when you analyze the properties of this transformation, it turns out that this is a degenerate FIO. It satisfies some of the basic properties, so it is an FIO. But in fact, it satisfies estimates that are not as good as the nicest estimates that FIOs can satisfy. There's a famous loss of 1/6 derivative associated with the geometry here. So very simple expressions can give rise to degenerate geometries and therefore analytical difficulties. Another example is a half-wave operator. So you can find an extended description of this, for example, in Chris Zog's book. So let P be a classical first-order SIDO. Again, I will define that in a few minutes. On a manifold X, say a compact manifold without boundary, elliptic self-adjoint with principal symbol, which is going to be homogeneous of degree 1 in its C variable, principal symbol P of X C. And an example of that is you have a Riemannian manifold MG, and you take the principal symbol simply to be the length of the covector C in the metric G at the point X, and that's the symbol of negative square root of the Laplacian, rather square root of the negative Laplacian, which is a positive operator. So in general, when you look at a half-wave operator, it turns out that you can write down an oscillatory representation of this form. So again, think of t as being fixed, for example, and you have a phase function which has a piece which is independent of t, and then you have another piece which involves t and the principal symbol of p. Okay, one more example, which is going back to the sort of prehistory of FIOs, which is this work by various people, including Maslov and Egorov. So these are what were called canonical operators and were a precursor to the more general Hormander theory. So let's start with what's called a generating function. So let's start with the function S of x eta, which is defined on Rn cross Rn minus 0. And it's homogeneous of degree 1 in eta, meaning positively homogeneous. So when you multiply eta by a positive constant, it comes out. So of course, those are typically not smooth at 0, as was mentioned yesterday. So you work on Rn with 0 taken out. So you have this function which has those properties, and you now impose a second-order condition, which is that the determinant of the mixed Hessian in x and eta be not equal to 0 at all the points that you care about, which is on the support of whatever amplitude you're going to be using. And then you write down this operator, which is basically you start with the Fourier transform of a nice function f, or a nice distribution f, Fourier transform at eta, and then you multiply it by a of x eta, the amplitude, and then you multiply it by e to the I s x eta, and then you integrate d eta. And when you put in the formula for the Fourier transform of f, you get this representation here, which again we recognize as the general form of an FIO. You have this phase function, but of this very special form, and then this stuff at the end. Okay, so again, this was an early version of FIOs. It was used by Egorov to prove his theorem. It was used to put certain kinds of PDEs into normal forms. But this kind of operator is simply too restrictive. This kind of phase function is too restrictive. There are many operators, especially generalized Radian transforms, things that come up in inverse problems, that you simply do not initially encounter in this form. You might eventually be able to put it into this form by some transformations, but this is simply too restrictive a class. Furthermore, hardwired into this, because of this assumption here, is that this is a very non-degenerate kind of FIO, satisfies the best possible estimates and algebraic properties, and that's simply not the case for general FIOs, so it needs to go beyond this, and that's what Hormander did. Okay, so those are some examples. Again, we won't actually rigorously define FIOs until one of the lectures tomorrow, but just to motivate some of what we're going to do here, before I go any further, let me define the two symbol classes that we'll be using, which basically were referred to in some form yesterday. Perhaps one of the exercises for the audience is to actually reconcile the various notations and terminologies that the various speakers use. So here we're just going to be using, for the most part, Hormander symbols of type 1, 0. There are also symbols of type rho delta, which many of you have probably seen. And the various theorems about FIOs and other things we'll be talking about all can be expressed in terms of symbols of type rho delta, except then you have some assumptions on what rho and delta are, and I don't want to do that. That's not appropriate for these lectures. So for the most part, we'll just be talking about symbols of type 1, 0, which means that every time you differentiate in a phase variable, you get a decay of 1. Here, this is the Japanese bracket that Shu-Wen referred to yesterday. This is 1 plus the length of theta squared square root. It's essentially the length of theta, except it's been smoothed off and made not equal to 0 near theta equals 0. And every time you differentiate in a spatial variable x, there's nothing changes. And now the constants here are allowed to depend on alpha and beta, the number of derivatives, but also depend on x ranging over a compact set. So there's no uniformity at infinity. If you were doing this on a non-compact space like Rn, the constants could grow at infinity, and we don't really care about that for our purposes here. Of course, if you were doing this on a compact manifold, then constants would be uniform. Okay, also it's important to notice here that the dimension of the underlying spatial variables x, I will usually call little n. The number of phase variables we'll call capital N, and in general, those two don't have to be the same. Okay, the second definition, the second space of symbols are the so-called classical symbols of order m. So again, m can be any real number. And the classical symbols are those functions a of x theta, which are actually, they are symbols of this type, but they're even better. They have these asymptotic expansions that Shu-Wen described yesterday. So A has an asymptotic expansion, A0 plus A1 plus A2, and so on. I won't write down again what asymptotic expansion means. And here AJ is homogeneous, truly homogeneous, of degree m minus j. So the top order term A0 is homogeneous of degree m, then m minus 1, m minus 2, and so on. And actually, all you really need is that this is true. It's homogeneous of that degree when the length of theta is, say, bigger than or equal to 1. In all of this kind of microlocal analysis, you really don't care what happens for theta small, basically because of the Paley-Wiener theorem. The inverse Fourier transform of something which is compactly supported is incredibly smooth and therefore does not show up in anything that we do. Okay. And as was mentioned in the talks yesterday, if you're given actually a sequence of functions aj of this form, then in fact you can asymptotically sum them through a Borel-style lemma, and there will be a symbol A in this class which has that asymptotic expansion. The key point here for us is that the principal symbol of this guy is actually A0, which is homogeneous of degree m. And for this class here, on the other hand, the principal symbol is really an equivalence class. The principal symbol lies in the quotient of Sm by the class Sm minus 1. And you sometimes have theorems where you assume that the operator is of this type, but you assume that it has a representative of its principal symbol class, which is homogeneous of degree m. But for the most part, we won't worry about the symbols. Okay, so now let's talk about the wavefront set, which was discussed yesterday, but let's reset the table here. So let's start with Rn. All of this will extend to general manifolds. So the cotangent space of Rn consists of pairs xc, where x is an element of spatial variable x in Rn, and c is a linear functional on the tangent space of Rn at the point x. In other words, it's a cotangent vector. Since I'm not a physicist, I won't call this a momentum, but you're free to think of it that way if you want to. And this has a distinguished subset, which is a zero section, which is where c equals 0. And since we're working in homogeneous microlocal analysis, typically we will work away from the zero section. So a subset sigma of t star of Rn minus a zero section is said to be conic if whenever you have a point in sigma and then you dilate the cotangent variable by a positive constant, it's still in sigma. So in other words, sigma is a union of rays in each of the cotangent spaces. So you also have a topology on t star of Rn minus 0, namely just the relative topology from t star of Rn. And we often talk about an open conic subset or a closed conic subset of t star of Rn minus 0. And an example of that would be if you have an nth order partial differential operator or an nth order classical SIDO, and you take the principal symbol and you take the characteristic variety, which is where the principal symbol vanishes, that will be a closed conic subset of t star of Rn minus the zero section. Another one is provided by the wavefront set. So let U be any distribution on Rn. This basically repeats the definition from yesterday in a slightly different form. So we say that a point x0, c0 is not in the wavefront set. So we're going to define the wavefront set by defining its complement, which will clearly be an open conic set, and therefore the wavefront set, its complement, is a closed conic set. So an element x0, c0 is in the complement of the wavefront set if and only if there exists a cutoff function phi of x, so in C0 infinity, not vanishing at x0. So now if you take u of x, which is an arbitrary distribution, and you multiply it by phi, you get a distribution of compact support. Its Fourier transform is therefore a real analytic function on all of C space. And you demand that the Fourier transform of phi u at C decays faster than 1 over any polynomial on some conic neighborhood gamma of C0. So not just on the ray of C0, but on a conic neighborhood of C0. And this notation here is a little bit fast and loose here. This means that for every n in the natural numbers, there is some constant Cn such that this is true. Okay, so you're not in the wavefront set if this is true, and everything that's left behind is a closed conic set that we call the wavefront set of U. And a basic example is the delta function, the delta distribution. So if you localize it using a bump function phi, at any point not equal to 0, you get the 0 distribution, whose Fourier transform is, of course, rapidly decreasing in all directions. If you localize it, no matter what the function phi is, because it's supposed to not vanish at 0, phi times delta is just going to be a constant times delta function. Its Fourier transform is constant in all directions, has no decay, and you pick up the entire cotangent space at the origin. Oops. So the wavefront set of delta is the entire cotangent space at the origin. So it'll turn out that delta is one of the prototypes for both a conormal distribution associated to the origin, and it's also a prototype for a Fourier integral distribution, or what's called a Lagrangian distribution, and because its wavefront set is in fact this space here, which is an example of a Lagrangian submanifold of T star of Rn. So we'll define these things going forward. So any questions at this point? Okay. So a few properties of the wavefront set. if you look at the projection from T star of Rn down to the spatial variable x, then the projection of the wavefront set can be shown to be the singular support of U. Right? So the singular support of U, just like the wavefront set, is a closed set, a closed subset of Rn defined really by its complement, which is open, right? And they fit together exactly in this way. And if you look at a PSI-DO of any reasonable type, no matter what reasonable symbol class it has, then it's a pseudo-local operator. It preserves the singular support, at least it doesn't make it any bigger. For any distribution you apply P to, the singular support of PU is contained in the singular support of U. And it's even what's called microlocal, which means the wavefront set of P of U is contained in the wavefront set of U. So PSI-DOs are very neat in the sense that they don't create new singularities. They preserve the existing singularities, possibly lose some of them, but don't create any new singularities. Okay, so everything we did so far was on Rn. We used the Fourier transform, but in fact, all of this localizes to a manifold. One needs to check the details, but all of this extends to facts about, to definition and facts about the wavefront set on a general smooth manifold. And again, you can, because this is a local concept, you can have a distribution not of compact support. The wavefront set is still defined. Okay, so now I'd like to ask the basic question of, if we look at other operators, other linear operators besides PSI-DOs, what do they do to the wavefront sets of the distributions that they act upon? Right? Now, of course, when you look at the properties of an operator, you want to know a lot more than this. You want to know L2 Sobolev estimates or LP estimates or other things. But this is one of the most basic things you can ask is, where does an operator send the singularities of a distribution that you're acting upon? Right? Many, I don't want to say most, but certainly many reasonable operators will turn a smooth function into a smooth function. Typically, they will turn singular functions or distributions into things with singularities. Where do those singularities lie? It's a basic question. Okay, so this is addressed by the Hormander-Sato Lemma. So let's suppose we have manifolds x and y. Suppose we have a continuous linear operator from distributions of compact support on y to distributions on x, which therefore has a Schwartz kernel by the Schwartz kernel theorem. So the Schwartz kernel is a distribution on the product space x cross y. And we can formally write the operator t as an integral operator with an integral kernel k. So if k were actually a nice function, relatively nice function, you would interpret this as in the sense of Lebesgue integration or whatever. But of course, this is interpreted weakly in the sense of distributions, but it's a convenient way to think about an operator. Okay, so we'd like to understand what such an operator does to the wavefront set of distributions that it acts upon. So the wavefront relation of T, which I think Andras wrote in a slightly different way yesterday, can be defined in the following way. So you start with the wavefront set of K. The wavefront set of K is a subset of T star of x cross y minus a zero section. And now what you do is you look for a four tuple x, y, c eta in the wavefront set of K, and you flip the eta to minus eta. So there's this operation of flipping the second set of cotangent variables, which permeates microlocal analysis. It's often denoted by a prime. So you look at four tuples such that x, y, c minus eta is in the wavefront set of K. And then you separate out the t star of x and the t star of y variables. So you simply rearrange things by grouping x and c together and grouping y and eta together. So this is now a subset of t star of x cross t star of y, and that's called the wavefront relation of t. So now the Hormander-Sato lemma is more general than what I'm about to state. I want to avoid technical difficulties, so we're going to make an assumption which is not always true, but will be true for the operators that we'll be discussing in these lectures. So suppose that the wavefront set of K actually avoids the zero sections on both the left and the right, by which I mean supposing that the wavefront set of the Schwartz kernel K consists of points x, y, c, eta, where both c is not equal to 0 and eta is not equal to 0. Now, you can easily think of operators where this is not the case, but let's assume this. Then this restricted version of the Hormander-Sato Lemma says that if you want to look at the wavefront set of t applied to a distribution u of compact support on y, then that's contained in, not necessarily equal because you can have cancellation of singularities, but it's contained in the following thing. You think of the wavefront relation sub t, the wavefront relation of t, you think of that literally as a relation from points of t star of y to t star of x, a relation just in the sense of set theory. So you look at the set of all points xc, which can be obtained by starting with the point y eta, which is in the wavefront set of u and is therefore a singularity of u, microlocally, such that xc is related to y eta through the wavefront relation of t. So you start with this subset, wavefront of u, this subset of t star of y. You apply this relation to it to turn into a subset of t star of x. That gives you an upper bound on the wavefront set of tu. So this is a really fundamental thing. And in some areas, for example, the application of generalized radon transforms and tomography and medical imaging and so on, even this very basic result has important implications. Okay. Now, if you iterate that, if you now have two operators, T1 and T2, what does this say? So supposing we have three manifolds, x, y, and z, and supposing T1 maps distributions on y to distributions on x, and T2 maps distributions on z to distributions on y, so that we can form the composition T1, T2. So supposing these two operators have Schwartz kernels K1 and K2, which are distributions on these two spaces, x cross y and y cross z, then the kernel of T1 composed with T2, which is provided by the Schwartz kernel theorem, is a distribution on x cross z. And if we assume that both of these operators avoid the zero section on both sides, so we make these assumptions here, then the wavefront relation of T1 composed with T2 is contained in the composition of the wavefront relations in the standard notion of composing relations between sets. So the wavefront relation of T1 composed with the wavefront relation of T2 consists of four tuples xc in t star of x, z zeta in t star of z, so that you can get from one to the other through an intermediary y eta in t star of y, so that both this is in the wavefront relation of T2 and this is in the wavefront relation of T1. Right? And now this too is a basic fact because as it turns out, what is a Fourier integral operator? A Fourier integral operator is an operator whose Schwartz kernel is what's called a Fourier integral distribution, which means it's given by a nice oscillatory integral. And the wavefront relations of individual FIOs are contained in what are called Lagrangian manifolds, or canonical relations. And it just so happens that when you form this composition of two canonical relations, under some geometric assumptions, you get another canonical relation. And there's a theorem that says actually when you compose those FIOs, you get another FIO. So you have an algebra of FIOs. But there are basic examples which come up in nature where, in fact, the composition of two canonical relations is not what's generally understood to be a canonical relation. It has singularities, it's nasty in some way, and that means that there's no general calculus for FIOs. And one of the interesting problems that's still out there is to develop a composition calculus for FIOs, which goes beyond what's currently known. And these things come up in applications quite frequently. Okay, so now let's talk about sort of a, yes?
What is true that wavefront set uses the zero section?
So an example when you might hit the zero section is if you think of going from distributions on Rn to distributions on a submanifold, and you try to restrict a distribution to that. Of course, you can define that operator on smooth functions, no problem, or even continuous functions. But in fact, you cannot define that for general distributions Because if you have a distribution whose wavefront set actually coincides with a normal vector to the submanifold, there's a problem. So that can be explained in terms of this, this setup, because the Schwartz kernel of that restriction operator is easy to write down. It's basically a product of delta functions. And when you write down what its wavefront relation is, it has a zero section on one side. So one problem that can come up is you're basically trying to do something which makes sense on smooth functions, but does not extend to distributions. There's a dual problem, which is when the zero section is on the other side, which is when you have an operator which you can define on any distribution, but even if you define it on a very, very nice function, you don't get a smooth function. So an example of that is actually the adjoint of the operator I just described. If you think of the operator that takes a smooth function on a submanifold and extends it into Rn by trying to multiply it by the delta function on the submanifold, there are problems with that, and that's due to the zero section problem. Right. So many commonly encountered operators don't have that problem, but you have to be careful. And in fact, whenever I'm doing a calculation, I run into a zero section problem, I swear silently, because typically it just means there's not going to be a clean statement. Right. Any other questions about that? Okay, so before we talk about general Fourier integral distributions, which really will be in the next lecture, and therefore Fourier integral operators, let's talk about this preliminary class, which are very, very nice associated to submanifolds of Rn, or more general manifolds. So these are so-called conormal distributions. So supposing we have the following setup, supposing that X is an n-dimensional manifold, and Y is a codimension K submanifold of it. Then the so-called conormal bundle of Y is a subset of T star of X, which simply consists of those pairs X, C, where X is a point of Y, and C is a linear functional on the tangent space, which annihilates the tangent space of Y. In other words, C, it can be thought of as being perpendicular to the tangent space of Y, although I emphasize this definition makes sense even without any metric. This is intrinsically defined covector restricted to linear subspace is equal to 0. Okay, so an example would be in Rn, if we write X as X prime X double prime, splitting the variables into the first K and then the last n minus K coordinates. If we take Y to be the copy of Rn minus K, which is obtained by setting X prime equals 0, then its conormal bundle consists of those XC's of this form, where X prime equals 0, that's what you need for X to be in Y, and C double prime equals 0, that's what you need for the covector restricted to the tangent space of Y to be equal to 0. And of course, this has a total number of variables of n minus K coming from this condition, plus K coming from this condition. So this is an n-dimensional submanifold of T star of Rn. In other words, it has half the dimension, and that's not a coincidence. The conormal bundle always has half the dimension of the ambient cotangent space. A particular special case is if we take Y to be the zero-dimensional manifold of the origin, then its conormal bundle is that thing we saw a couple of slides ago for the wavefront set of the delta function. It consists of T star of Rn at the origin and nothing else. And in homogeneous microlocal analysis, typically you'll take the conormal bundle of Y and then take out the zero section. More generally, if you have Y, which always locally can be described by defining functions phi1 up to phi k on our ambient manifold X, where we always, whenever I say defining functions, I assume that these guys have linearly independent gradients, then the conormal bundle of Y just consists of those pairs X, C, where X is a point in the submanifold Y, and C is a linear combination of the gradients of the phi j's. Yeah. Any questions about that? Okay, so now let's talk about some examples of conormal distributions before we define them. So many of the classical distributions you'll see in any textbook on distribution theory, for example, the 5-volume work by Gelfand and Shiloff and company, many of these distributions are conormal distributions. So examples would be on the real line. The Dirac delta function is conormal for the submanifold Y, which is the origin, as are various analytic or meromorphic families of distributions that are related to the delta function and which come up frequently in scattering theory and harmonic analysis and so on. So you take the positive part of x on the real line, raise it to the z power that has a well-known meromorphic continuation in z. Same thing for x minus to the z, or x plus or minus I0 to the z. These are all entire or meromorphic valued functions of z in the complex plane with values not just in distributions, but in distributions that are conormal for 0. Another example would be the Dirac delta function Rn is again conormal for the origin now. 0 is the origin in Rn. And the Newtonian potential, whether given by this formula in dimensions 3 or higher or by the logarithm in 2 dimensions, the Newtonian potential is also conormal for 0, although in some sense 2 derivatives smoother than the delta function. Okay, so again, if we look at this general setting where you have defining functions phi1 up to phi k for a submanifold Y, then if you have so you think of phi as a function from Rn to Rk, and now supposing you have a conormal distribution for the origin in Rk. It could be the Newtonian potential, it could be the distance to the origin in Rk to some power, it could be something else. If you have something which is a conormal distribution for t equals 0 in Rk, then you can form the composition u of phi, and that gives you a distribution which is conormal for y, which is being defined by these functions phi1 up to phi k. And there are many examples in Gelfand and Sheloff of this type. So you start with a nice polynomial. It could be a linear function. It could be a quadratic function. You take that, and you take that plus I0 to the zth power, or you take its positive parts to the zth power. You analytically continue it. Those are conormal distributions. On the other hand, if you have a submanifold Y with singularities, like the light cone, then typically that will take you outside of the class of conormal distributions because of the singularities of the submanifold. Yes? Okay, so it's not time, it's actually, so t here is, you have a function phi, which should have been a little phi actually. So little phi is phi1 up to phi k. You can think of that as a family of defining functions. You can also think of it as a vector valued function. So t here denotes an element of Rk, right? So if you have a conormal distribution for t equals 0, so t doesn't mean time, this means t is an element of Rk. So this is a conormal distribution for the origin. It could be like the delta of t on Rk, and you can form the composition u of phi. So so supposing you have this submanifold Y contained in Rn, and it's described by as the preimage of 0. So this is t equals 0 as an element of Rk, right? Right, so I said these are defining functions. So the fact that the gradients are linearly independent means that this is a submersion. That's exactly right. And so y here is being expressed as phi inverse of 0. So it's the preimage of 0 under a submersion. So this guy is a nice, smooth submanifold, right, in Rn. And I'd like to describe a distribution on Rn in the following way. 0 here is sitting inside of Rk. And now there's a family of distributions on Rk which are conormal for the origin. It could be the delta function. It could be the length of t to a power, right? So if you raise this to the z minus k power, when the real part of z is bigger than 0, this is a locally integrable function and defines a distribution that's actually a conormal distribution for the origin. But you start with anything which is a conormal distribution u over here, you can then form the composition u of phi, which is a distribution over here. Right? In particular, if you start with the delta function, you would get delta of phi, which is sort of the most basic example of this operation. And delta of phi is simply a smooth multiple of surface measure on y. You know, this delta of phi is really a measure mu, which is a singular measure on Rn, but is supported on y. Yeah, so t here is not a time, it's an element of Rk. Any other questions? Okay, so now we're going to define conormal distributions in two ways. So this is motivated by, actually relevant for this example here, is on Rk, if you look at the delta function, and you look at the Fourier inversion formula, which does not converge pointwise, would make sense in the sense of tempered distributions, the Fourier transform of the delta function is 1, and therefore delta of t is an element of Rk, has this representation, or I actually remember the power of 2 pi. It's the integral over Rk of e to the ix dot theta times 1, and we think of 1 of theta as being a symbol of order 0 in theta. So now we want to think of this representation and generalize it. We want to possibly change the symbol 1 of theta to a general symbol, not necessarily of order 0. So it could be a symbol a of x theta. Oh, this should be a t. Sorry about that. E to the I t dot theta. My bad. And we want to consider a phase function here, which is somewhat more general. Now that phase function there, which should be t dot theta, is a summation theta j tj, j going from 1 to k. We'd like to replace that with similar phase functions, but where you don't need to have the coordinate functions t1 up to tk, you can have other functions as long as they satisfy that submersion condition that they have linearly independent gradients. So we make the following definition. Suppose we have an n-dimensional manifold X, we have a codimension K submanifold Y, given by a collection of defining functions phi1 up to phi k. Again, defining function meaning that they have linearly independent gradients. Then a distribution u on X is conormal to Y of order m, and I'll make a comment about the order here because it's a little bit non-standard. If it can be written as an oscillatory integral, an integral over Rk, and the amplitude A of x theta, the amplitude I'm going to take to be of order m. So here I'm not using Hormander's formula for what the order of distribution should be. This is simply being lazy and saying that it's conormal of order m if the amplitude is of order m. So the delta function is of order 0 because 1 of theta is of order 0. And the phase function here is the linear combination of the phi j of x's with coefficients theta 1 up to theta k. So you're forming sort of the generic linear combination of the phi j's using the phase variables phi1 up to phi k, and that's where your phase function is. Okay. So as was described yesterday by Xu Wen, the integral need not converge pointwise unless the order of A is sufficiently negative, but there's a way, which I'll get to in a moment, to interpret this in the sense of distribution. So this always makes sense for a symbol in this class or any reasonable symbol class. Okay, so one more thing to say about the phase function is that this phase function is linear in the phase variables theta 1 up to theta k. And that's really what distinguishes conormal distributions. The phase functions are not just homogeneous to degree 1, they're actually linear functions in theta. Okay, we now let Im of x semicolon y denote the class of distributions on x, which are conormal to y of order m. And if we drop the m, that means the union over all values of m. So all conormal distributions of all orders, things that are distributions on y, conormal for distributions on x, conormal for y, we denote simply by this. And as I said, if you're just working with conormal distributions, this way of labeling the order is very convenient. It does not agree with Hormander's definition that we'll get to in a future lecture, but it's just convenient if this is all you're working with. Okay, now that was the the definition. But now we have a second definition, or it's a proposition, whichever you want to think about it, that the first definition is equivalent to the second definition. So the following is true. Let me state it as a proposition. So U is in this class I of x, y. So it's conormal for y of some order. If and only if there exists S naught in R such that U is a Sobolev function locally of order S naught on X, and it satisfies the so-called iterated regularity condition with respect to the family of vector fields that respect the geometry of Y by being tangent to Y. So what does that mean? So for every natural number n, and all smooth vector fields V1 up to Vn on the manifold X, so on the ambient manifold X, that have to be tangent to Y, which means off of Y you don't care their value, but at Y they have to be tangent to Y. Then if you take the distribution U and you differentiate it capital N times using these vector fields, ordinarily if you apply a first order operator to an element of HS naught, you lose one derivative every time you apply the operator. But what we demand here is that, in fact, you have a stability, which is that the Sobolev regularity never changes. Okay, so that's the iterated regularity condition, and this can be taken either as a consequence of the definition on the previous slide, or this could be taken as the definition of conormal, and then you could give the previous definition as a consequence of this. They're equivalent. Okay, so this notion, I believe, goes back to Boney and Melrose in the late 70s and early 80s. If you want to really nail down the relationship between S naught and the order M, in fact, you should not use Sobolev spaces, but you should use Besov spaces, BS to infinity, but I won't do that. Okay, so let's give an example of why these two things are equivalent, or at least in one direction. So let's take our standard example of Y being the origin and Rn. Then the set of vector fields that are tangent to 0 is simply generated as a module over C infinity. It's generated by these vector fields Vjk. Vjk is simply taking ddxk, which of course is a basis for the tangent space, multiplying by the functions x1 up to xn, which vanish at the origin. And any vector field which is tangent to the origin is a linear combination of these guys with the smooth coefficients. Okay, so we only need to examine one of these guys. The smooth coefficient multiplying by that doesn't change HS naught, so that can be ignored. So we just have to ask, why is it that these vector fields here preserve things that are conormal for the origin? So we start with the oscillatory integral from the previous slide, which represents something which is a conormal distribution for the origin. Let's apply this to it. So first, let's apply the differential operator ddxk. It passes inside the integral. Again, this makes sense when you interpret these oscillatory integrals in the sense of distributions. You pass the ddxk inside, and it does two things. Either differentiates the phase, which brings down a I theta k times A, or it differentiates the A and replaces it by the xk derivative of A. And now when you bring the xj inside, you're simply multiplying by xj, you notice that xj is nothing other than 1 over I times the theta j derivative of e to the I x dot theta. So you represent multiplying by xj by that. And now you integrate by parts in the theta variable. That's, again, justified in the general theory of oscillatory integrals as distributions due to Hormander. And so when you integrate by parts, actually, I'm not even doing that, actually. I'm sorry, I am. I'm integrating by parts here. I throw this guy over here. So this guy here, when you differentiate in a spatial variable, the order doesn't change. This guy was already of the same order of A. This guy was of order 1 worse. But now when you differentiate with respect to theta j, because the integration by parts, I lower the order back down again to m. So whatever order m A originally had, this guy has this form where B has the same order m. And now it's a basic exercise to show that if you have any oscillatory integral of this form, you can put even just a crude bound on what Sobolev space HS naught belongs to in terms of the order m by doing some calculations. So as long as you preserve the order m of the amplitude, you preserve the Sobolev space, and therefore you have the iterated regularity condition. This, of course, is just one application, but no matter how many times you apply these vector fields, the same thing happens. Right? You can also go backwards. If you have the iterated regularity characterization with respect to these vector fields, one can actually do some work using Sobolev embedding and show that, in fact, you have an oscillatory representation where A is a symbol of order something. Okay, so we have these two different characterizations of conormal distributions. And now let's discuss the wavefront sets of conormal distributions. So there's a proposition which says that if you have a distribution conormal for y, then its wavefront set is contained in the conormal bundle of y. And again, I'm deleting the zero section because the wavefront set is defined as an element, as a subset of the cotangent space minus the zero section. Okay. Therefore, projecting down, you get that the singular supportive u is contained in y. So conormal distributions are singular only on y, but more precisely, their wavefront set only points in the direction of the conormal bundle of y. Now, just as a little bit of a warning here, in general, it's not the case that just because you have a distribution whose wavefront set is contained in the conormal bundle to some submanifold, it's not the case that u is conormal for y. There's a basic example due to Hormander of a distribution whose wavefront set is along a single ray. It's a single point x naught in Rn and pointing along a single ray. There are many submanifolds y that ray is contained in the conormal bundle of, but that distribution, which is somewhat exotic, is not in any standard conormal space. Right? However, if you're doing sort of, you're working on some problem and you find some distribution whose wavefront set is contained in the conormal bundle, it's pretty likely that it's actually conormal. So, for example, if you have a smooth density, a smooth multiple of surface measure on some submanifold y, you can write that essentially by using Fourier inversion in RK. You can write mu of x in this form, as I was doing on the board over there a few minutes ago. And therefore, the wavefront set of surface measure on a submanifold is contained in the conormal bundle. The same thing is true for all these other distributions you'll find in Gelfand and Shilov, things that are associated to submanifolds by taking defining functions and composing them with positive parts to a power, things like that. Okay, so let me just wind up by quickly zipping through the wavefront relations for the various operators that most of the operators we began with at the beginning. So if you look at PSIDOs, then the Schwartz kernel of a PSIDO is given by this expression here, and therefore the wavefront relation, since this is associated to the diagonal, this is conormal for the diagonal x equals y in Rn cross Rn, or x cross x on a manifold, the wavefront relation is contained in the so-called diagonal relation xc, xc. Right? If you look at pullback or composition with a diffeomorphism, same thing. The Schwartz kernel is simply given by this expression here, and the wavefront relation is contained in the set of all four tuples xc, and then chi of x, and then the contragradient of the differential of chi. So that means d chi transpose inverse applied to c. And this is an example of a canonical transformation. xc goes to this. Okay, you can do this for the Radon transform. I won't go through the details here. This allows you to predict where the singularities of the image under a CT scan, if you have singularities in somebody's body, like a broken bone or something, this will tell you where the singularities will show up in the data. You can do the same thing for the spherical mean operator. Melrose-Taylor transform. Again, these slides will be online. But let me finish up by talking very quickly about the wavefront sets of oscillatory integrals. So Fourier integral distributions are special kinds of oscillatory integrals where you make some assumptions about the phase function. And so we're interested in phase functions which have the following properties. They are, say, a phase function on x cross Rn minus 0. And again, capital N need not be the same as the dimension of x. Real valued, smooth away from the 0 section, positively homogeneous of degree 1 in theta. And now we impose a first order condition, which is that the full gradient of phi is never equal to 0. So there's at least some partial derivative either in an x, j, or a theta k. There's at least one partial derivative of phi, which is always not equal to 0. The order of the quantifiers is wrong. At every point, there's at least one partial derivative, which is not equal to 0. Okay, so proposition. So these are oscillatory integrals in the sense of Hormander. If phi is such a phase function, and a is any reasonable symbol, say SM10, then the oscillatory integral of this form, which again typically will not converge because the order of a won't be negative enough, this is still a well-defined distribution. And the way you define it is pairing u against the test function f of x is defined as this integral here. And this integral here is defined by an integration by parts argument, which due to the time I will not give at the moment. I may begin the next lecture may begin with this, that Raluca gives tomorrow. And then let me just conclude by saying that basically the same argument that shows that this makes sense as a distribution, if you modify it a little bit, if you microlocalize it a little bit, it gives you an upper bound on the wavefront set of such a distribution. Namely, the wavefront set of u is contained in this very important object we'll call lambda sub phi. And lambda sub phi is the following. It's a set of all pairs x comma dx phi. So dx phi is intrinsically a cotangent vector at x. So it's a cotangent vector. So you look at the pairs x comma dx phi where x theta is such that the theta gradient of phi is equal to 0. So basically this condition here gives you what's called the critical manifold of the phase function. And you take the critical manifold, which lives in x cross Rn, and you transform it into a subset of t star of x. And this first order condition guarantees that if this is equal to 0, this is not equal to 0, and therefore this actually resides in t star of x minus 0 section, and in fact is a conic subset. Okay, so for oscillatory integrals of this form, with this condition here, these make sense as distributions, and you have an upper bound on their wavefront sets. And now what one wants to do next is to define Fourier integral distributions by imposing a second order condition, strengthening this by imposing an additional second order condition, which guarantees that in fact lambda phi is a very nice submanifold of t star of x. In fact, it's what's called a Lagrangian submanifold, and therefore these will be called Lagrangian distributions or Fourier integral distributions. Okay, that's all for today. I guess with some abstract result, you probably can form anything out of the delta function, either through differentiation or linear superposition of translates. It's certainly the simplest. I mean, its amplitude is 1 of theta, so it's independent of x, and it's constant in theta. Yeah. Yes, I mean, it's sort of a tautology, perhaps. But yes, so I guess the answer would be actually, so you probably could do it with this IDO. So given any conormal distribution, say for the origin, it could be expressed as a PSI-DO acting on the delta function. But again, it's almost like a tautology. Right? Yes?
Are there classes of symbols that will include the phase function, the S110, but away from 0?
S110. We do.
Are there some classes of symbols that will include phase functions?
No, so phase functions.
Phase function is not
Right, so actually, so in the definitions of the symbol classes, I didn't write it down, but basically you can just ignore anything within theta less than or equal to 1. Yeah, so yeah, it's certainly the case that since phi is homogeneous of degree 1 in theta, you could think of it as a classical symbol of order 1.
Yeah.
Right.
What is the topology then? If you move stuff away to 0, what is the topology?
So there's, I didn't say this, there's a collection of semi-norms, right? There's a Fourier topology on these symbol spaces. In order to do that, you would need to insert some cutoff function and say that once you've multiplied by this cutoff function, which kills everything near the origin, then you have these bounds on the derivatives of the function. So the topology would be whatever Fourier semi-norms you're using, you would simply apply it to the phase function, and it would be a symbol of order 1. It would be a classical symbol of order 1.
So you get equivalent classes modulo stuff near 0.
Yeah. So the thing, there is this. You have to make some arbitrary choices of what cutoff function you're going to use, right? Typically, except maybe for very specialized problems that simply would not come up. Again, those things really contribute just real analytic, not just smooth, but real analytic errors to whatever you're doing. Any other questions? Yeah. Yeah.
You had these Schwartz kernels which did bad things. You mentioned that
Yeah.
good things, the bad things, and things like that. So one example that will come up this afternoon. So in scattering theory, it's a fairly typical state of affairs that we think of floating principle or in dynamic systems. Started something very nice, apply the like Schwartz, apply the resolvent to it, and you get something excludently resolvent, you get something singular. So that's connecting to other aspects of the version.
Right. So the zero section problem can come up in unexpected places, and it's an annoyance.